All right, so let's dive into Unit 11. This is topic 11.1. This is going to be focusing on electric current. So all the way up until this point, the charges have just kind of been shifting around. They haven't been allowed to flow. Yes, I know we talked about grounding, that the charges flowed from from the ground up and so forth, but that was the extent of their motion. So now we're going to let those electrons to freely move through a conducting wire. Okay. So I apologize for everything popping up at once. My slideshow, for some reason, did not like this. So current is going to be the rate at which charge will pass through a cross-sectional area of a wire. This actually ends up being a derivative. So current is I, then you have is equal to the derivative of Q dt. So if you're given a function for Q, then you can determine what I is, all right? But if you're given something for I, you can, rework our calculus and write it as an integral. So Q is equal to I dt. Now, within that conductor, every charge carrier, i.e. the electrons, are going to have what we call an average drift velocity that is going to be related to the amount of current that flows. So we have another equation for current. Okay, and the main thing in this equation is that V subscript D. That V subscript D is what we call drift velocity. And basically what that is, that's the amount of, that's how fast the electrons are moving through this, through the conducting wire. Okay, N, maybe another confusing thing, that's just the number of charge carriers that are in this wire. So electric charge will move through the circuit in response to the potential difference, which we sometimes call the electromotive force, or EMF. Okay, EMF or electromotive force is just a fancy way to say the voltage source. Now there's going to be a difference between voltage source or voltage and EMF, and we'll get into that here in a little bit, especially when we talk. I think it's going to be in a couple videos. All right. Now, a lot of this slide is just going to be focusing on the amount of current that is there, and so we're going to write a lot of equations for current. And so current density is the flow of charge per unit area. All right, so the way you could think about current density is very similar to like flux, right? The amount of charge, the amount of current that's flowing through this unit area. And that's what J is, okay? And we can, again, it seems like we're just going to write these kind of equations, but if you look at this equation right here, the first part of it is J. So that N Q V sub D, that is J. Because if we were to, solve this out, we would get current equals J times A, right? And so that's where we get this idea that J is just simply that NQV sub D. Now, the potential difference across the conductor, right, again, remember, creates electric fields. And so that is going to be proportional to the resistivity of the material and the current density, or E is equal to rho J hat. So this rho is not the rho we've been talking about in terms of volume charge density. This is the resistivity of a material. It is a known value for the materials, and it leads to resistance, which we'll get into when we talk further into circuits and Ohm's law. Now, if a function is given for your current density, the total current can be determined by integrating the density over an area, right? So that current density. Oh, sorry, dA. Most wires have a cross-sectional area of a circle. And so simply, that dA ends up being something like pi r squared dr or something along those lines, okay? Or 2 pi r, sorry, not pi r squared. That would give us a volume, but it would be 2 pi r dr, right? That would lead us to the area equation. Now, current is a scalar quantity, but it does have a direction. And the way we talk about this is this conventional current, and it's chosen to be in the direction in which positive charge will move. But we know positive charge does not move, but it's actually opposite the motion of what actually happens. And the current is actually due to the movement of electrons. Now, don't let that confuse you, because what happens is we always flow out of the positive end of the source into the negative end of the source. So that's why we say like it's chosen to be in which direction the positive charge would move. Okay. Now let's look at an example. So we have a long conducting cylinder with a radius of r, as shown in the figure. It carries a current to the left. So our current is going to be traveling in that direction. The current density varies with the distance r from the cylinder's central axis according to the equation J equals kr squared, where r is less than or equal to big R, and k is a positive constant. Now what we're going to do, again, classic AP Physics C question, derive an expression for the total current in the cylinder. Okay, so this is kind of that last equation that we were talking about, where if you're given a function for J, right, you're going to simply integrate J with as a function of R dot dA. And now we just kind of substitute in what we're given, right? So they tell us that J is kr squared, right? So that's that. And then dA is 2 pi r dr, right? Because it's a cross-sectional area of a circle. So that's why we're going to, so we take the circumference of the circle and we integrate it through that circumference, and that gives us the area. And now, if you've never done derivatives before, integrals before, rewrite and combine. So 2 pi k, those are all constant values. So I'm going to pull them out of our integral. And this is going to go from 0 to big R. And that just leaves me r squared times r, which gives me r cubed. And so I'm integrating r cubed. Okay. Now we use our basic power rule, plus 1 over 3 plus 1. And so we're going to get 2 pi k. And our answer is going to be r to the 4th over 4. And we're evaluating that from 0 to r, which again just means I'm going to substitute in capital R and 0, right? So 2 pi k integral big R to the 4th over 4 minus 0 to the 4th over 4, which is good because the great thing with it being 0 is that's just going to be 0. And our answer is basically right here, right? So the current that is flowing through this cylinder is 2 pi k big R to the 4th over 4, okay? But we can do some simplifying. That 2 cancels one of the 2's and the 4. So our final answer would be pi k over 2 times r to the 4th. Highlight that. So there is our answer, right? So the current is equal to pi k2 r to the 4th. All right, so in the next video, we're going to shift from talking about current to now what happens when it encounters things to use that current.